All right, let's get started. You remember the fundamental theorem of line integrals?
Yeah. Do I?
Boundaries? When we started talking about Green's theorem. Green's. So the fundamental theorem of line integrals tells us that if we had a conservative vector field, then our integral over a curve of that conservative vector field, which we will write with a potential function, the gradient of the potential, dotted with ds, is equal to the original function evaluated at the boundaries, and the boundaries would be the endpoints in this case. So assuming that we parameterize C with R, we can write this at the endpoints. So that means it doesn't matter how we get from point RA to RB, as long as those are the boundaries, as long as the boundary is RA and RB, as long as we get there, that's still going to be your boundary, so it doesn't matter how we get there. I'm just repeating myself now. I just wanted to stress the fact that it doesn't matter what the curve is, as long as the boundaries still the boundaries, then that's all good. Yeah? Oh, yeah, I don't know them off the top of my head. Here are the conditions. So in our last class, we did this example. Do you remember this example? So Stokes Theorem says that we can take the flux of a curl of a vector field and bring it down to a line integral over the boundary with a positive orientation of the original function. All right? So this is the surface that we're dealing with is this hemisphere that pointed to the, not pointed, but it opened to the negative y. I think there was people that had issues in my drawing the other day. That looks like a hemisphere, right? Opening sideways. Oriented in the direction is positive y, so the orientation is positive y. And then we said that this orientation for the surface gave a positive orientation for the boundary going in this direction. Right? So we have this line integral, and this is the boundary of the line integral. And suppose instead of looking at the surface as a hemisphere, now let's suppose we consider another surface that might be easier to deal with that has the same boundary with a positive orientation. Like maybe a disk. And if we want to keep that same orientation, then our orientation would still be pointing in the positive y direction. So now if we take Stokes theorem from the line integral to a flux integral, a flux of the curl, with an easier surface to deal with, then that might be an easier computation to make. Yeah? Would you agree?
Yes.
Wasn't there a 10-second rule? So what we're saying is that this flux integral that you would do over the surface can be changed into a line integral that you would do over this boundary. But if you can make up another surface that's easier, that would give you the same boundary, then maybe you can do this simpler integral over a new surface that would have the same boundary, and then it would be a flux of the curl again. That's kind of like this whole path independence business. All you're concerned about is the boundary, the endpoints in this case, A and B. Doesn't matter how you get there. So if we were to compute a line integral, do this from scratch with a line integral, I probably want the easiest way to get there is a straight line. Well, if your boundary happens to be a circle, maybe the easiest surface to deal with would be a disk. Right? So I think our answer was negative pi for this. Let's do this computation to see if we're going to get the same answer if we do it with this disk. So let us parametrize this disk. And let's call the disk, this is surface, right? So let's call it capital Phi. And And this is going to be a disk on the xz plane, so that would give you a y component of 0. And then this disk can be parametrized. Let's do the parametrization. Let's see, z. I'm going to do it with polar coordinates this time. I think I've been kind of avoiding polar coordinates, but let me do polar coordinates. And I'm going to let the z be the cosine, and then the x be the sine. And if we take a look at the orientation for this, you'll see that it should be going in the positive y direction. So let's let our phi of r be cosine, so r cosine theta 0, r sine theta. Oh, that's a negative. Our phi of theta. Wait, I did that wrong, didn't I? So the derivative with respect to r, this is sine theta, and this is cosine theta. Now with respect to theta, this is where I get the r cosine theta and negative r sine theta. So if I cross them, looks like I'm going to get 0 and 0 for my x and z. And then if I look at my middle term, it'll be minus, oh, it's negative. I didn't do my orientation correctly. Minus r sine squared theta minus r cosine squared theta. So you'll have the sine squared and cosine squared to equal to 1. Bummer, I thought I had this right. So it looks like my orientation here is the opposite. It's negative r. So this is... What?
Shouldn't it be correct though? Because you're going to the circle you parameterize it so that it would go clockwise and counterclockwise.
That's what I would think. Oh, yeah. So now it would be positive. Thanks, Woody. So now it's positive. So the thing is that there's 0, 0. That makes sense because my normal vector should be going just in the y direction. No, nothing going up and down. And then the r, I didn't put this down, but the r is, for us, in polar coordinates, is always positive. So a positive r is going to give us a positive y direction. And so there's our business. Okay? All right, so that's our setup. And now we need to take the curl of f. I think we took the curl last time. We got -1, -1, -1. So let's finish this computation. We got -1, -1, -1 for the curl. The ds is going to be this vector, the cross, 0, r, 0, and then we're going to go dr d theta. Do we need an r dr d theta here? No.
Damn it. God, I did it wrong. God damn it.
If you use this parametrization already, the extra r from the r dr d theta comes out of the cross product already. Yeah, exactly, because that's what the parametrization does. It accounts for that. And so your R comes out automatically from the cross product. Yeah. So our domain here is a nice square now that we're in polar coordinates. So then we can set up our integral to be an integral from 0 to 2 pi for theta, integral from 0 to 1 for r, negative r, dr, d theta. So negative r is negative r squared over 2 from 0 to 1, and then you multiply this by theta from 0 to 2 pi. So that's negative 1/2 times 2 pi, which is negative pi, which is what we got yesterday. That's next. Yes. Okay, is this good? So now the power of Stokes' theorem isn't just this connection between a surface or a flux integral and a line integral, but also the fact that no matter how complicated your surface is, if you're finding the flux of the curl over some complicated surface, you can either compute it over its boundary, or you can simplify the surface into something that would be simpler. Simplify. You can integrate over a surface that's a lot easier to deal with than the original surface, as long as it has the same boundary and as long as it keeps the positive orientation. Okay? Is that good? All right. So Caesar kind of jumped the gun on my next topic, and that is to take a look at the flux of the curl and let's imagine this going down to 2 dimensions. So this is 3D. And in 3 dimensions, 2D is just a special case, right? So let's consider this in 2 dimensions. So what's that say about our F? Our F now should only have 2 dimensions. F1, F2. Oh, let's use P and Q. Right? Or if you want, P, Q, and 0. Yeah.
So I'm confused because how can you consider it in 2 dimensions when you have a plane, but your area vector is going to be perpendicular? So it's going to be automatically in 3 dimensions.
Yeah.
Okay.
So we'll keep it in 3 dimensions just by putting zeros here, and we'll see what happens. Since we are in 2 dimensions, we're bringing this down to 2 dimensions. You still live in 3D, right? And then you're just looking at this from a 2-dimensional point of view. So when you are looking at this from a 2-dimensional point of view, then the P and Q are just functions of x and y and no z's in it. And now your surface, instead of a wild surface in 3 dimensions now, this is probably just get dropped down to a 2-dimensional region. We'll call D. forgot my arrow on the little s, big S there. So let's take the curl of f. If this is my f function, I'm taking the curl of this. The derivative with respect to x, or no, my x component is going to be the derivative of 0 with respect to y, and then the derivative of q with respect to z. What's the derivative of q with respect to z? 0, because q is a function of x and y. There are no z's in there. With respect to y, the middle term, we got the derivative of 0 with respect to x, and then the derivative of p with respect to z minus, which again should equal to 0. And then the last component is the derivative of q with respect to x minus the derivative of p with respect to y. That's Green's theorem, right? Well, at least that's what goes into a flux integral, but this is right now, well, in Green's theorem, it was a double integral, right? Now we have a flux. Let's see if we can put these components in to make it into actually make it into a double integral. So we need to parametrize the surface. That's kind of weird. Let's say your region, your two-dimensional region, looks like this. That's flat on the xy plane, right? So if you were to parametrize this, you can just say, well, we'll keep the x as the x, the y as the y. And then what would the z be? The z would be 0 because it's flat on the xy plane. Right? So here are our two independent variables, x and y, and we'll keep our domain D to be our limits of integration. So phi of x, or phi sub x, the derivative of phi with respect to x is 1, 0, 0. Taking the derivative with respect to x of the parametrization. The derivative of phi with respect to y is 0, 1, 0. So what's the cross product of this? What is it? 0, 0, 1. So that would be your ds. Right? So your k vector, this is really your k vector, right? It's just going straight up out of 2 dimensions to the 3rd dimension, but that's essentially what your ds is equal to. So what we have here is our flux integral now is going to become a double integral of 0, 0, and then this thing. Dotted with 0, 0, 1, sometimes called the k vector, dA, dx, dy, dy, dx. And that becomes partial of q with respect to x minus partial of t with respect to y dA. So that's half of Stokes' theorem now looking like Green's theorem. This is the regular Stokes' theorem. Stokes' theorem in vector form, or Green's theorem, sorry. Green's theorem in vector form looks like this. So, yeah, so you're really taking the curl and then you're dotting it with a k component, dA. So that's sometimes you would see this that looks a lot like Stokes' theorem, but it's really Green's theorem because it's in 2 dimensions. Okay. Now the other half of it is the easy part. Well, kind of. Because now you're looking at the integral over the boundary. And then, so one thing to make sure of is that our boundary has a positive orientation. So the orientation, because this is flat on the xy plane, it's easy for us to just say the orientation is going counterclockwise, right? So the hard part about going up in space in 3 dimensions is that you can see these curves from different points of view, so the idea of counterclockwise gets a little weird. What I'd like to think about with Green's theorem is that the orientation of the curve, when you walk along the boundary of that domain, as I'm walking along that boundary of the domain itself is on my left side. Does that make sense? Think about it. I'm walking over here, and as I'm walking the boundary, as I'm walking on the boundary, the region itself is on my left side. Okay? Yeah. Right. The lake is on the inside. It's on the left. So a more difficult thing to think about is that if I'm walking along this boundary in 3 dimensions, this is kind of weird now, but as I'm walking around this boundary, the side of the surface with a positive orientation is on my left side. Look, I'm walking along this boundary, right? I'm walking along this boundary. The side where I see my normal vectors is on my left side.
Are you walking along? Are you walking along the side off, like on the ring?
I'm walking along this.
Or the other same side as the surface?
I'm walking along. It doesn't matter if I'm walking along. So I can be. If I'm walking in the direction, in the positive direction, I guess I should have drew that guy over here. If I'm walking along this, regardless of where I am, right? If I follow my left side, that's where I'll see my positive vectors pointing out. It'd be easier if I was walking on this one, right? I'd be walking along this way, and then the normal vectors are pointing out on the left side of the surface. It's all right, Henry.
On that first picture of the hemisphere, where the side the man is on with the arrow, is that towards us or is that back into the board?
Doesn't matter. It could be. It would be in the front part right here.
Okay.
And then as you're walking along there, going in this direction, then the normals will be pointing out on my left side. That was a little bit harder to think about. If you could just remember the right-hand rule, that's fine. But yeah, if you're walking along here, the inside of that region is on my left side. And if we use this F as P and Q, right, and then the ds is the x prime and the y prime, then that all just kind of simplifies, because there's a lot of different ways to write our line integral. That then just simplifies to the boundary of D, a line integral. It's a closed line integral of P dx plus Q dy. And this is how we saw Green's theorem the first time, which is really a special case of Stokes, because Stokes is in 3D and this Green's theorem is in 2 dimensions. Okay. Green's is Stokes, but in 2 dimensions, yes. Yeah, you could say that. But they're all, oh, I don't know. It's hard to say more general form of the fundamental theorem. It's just another form of the fundamental theorem. Not necessarily more general. It generalizes Green's theorem to higher dimensions. Yeah?
Is there a special case of Stokes? Is Stokes a special case theorem for something higher than
No. I'm sure people have developed higher dimension integrals, like a flux integral in 4 dimensions would be something kind of fun, weird. Yeah, let's do more Stokes problems. Let's take number. Do you have a question?
Yeah, I'm having trouble just thinking about, so I understand why you would use the regular flux integral without the curl. What is the purpose of
The flux of the curl?
Yeah.
It comes up every now and then. That video that I was showing earlier, they talk about why you would want to compute the flux of a curl. And I can't really explain it because I don't know why. I just do it because I'm a math person. But it does come up in Maxwell's equations.
Oh, really?
Yeah.
Okay.
So. And I'll try to take a look at a couple of those equations. We might actually be able to derive with the stuff that we know. We'll take a look at it. Let's take a look at this problem where we have f of x, y, z is equal to this vector field. And S contains the top and the 4 sides, but not the bottom of a cube with vertices at plus and minus 1 all the way around. So, if you take a look at the vertices, I would need to deal with 5 surfaces if I were to do the regular flux of the curl here. Got the 4 sides and then the top, but the bottom is open apparently. So in terms of computing the flux of the curl of this vector field over the surface, I don't want to do 5 surface integrals. I don't want to do 5 flux integrals, right? So now let's bring it to the other side of Stokes' theorem. which is that boundary. So the boundary is this orientation would be going this way. So the boundary of S will consist of 4 lines. Yeah?
Why can't you just take, if it's open, why can't you just close the box? And then take the surface of the box, the surface of the lid.
Yeah, I was getting there. So I would have to, if I were to use the line integral side of Stokes Theorem, I would have to parameterize 4 lines and then take the line integral over this surface, over this vector field. So why don't we do what AJ suggested? She didn't let me finish. And why don't we consider, so this is the trick about Stokes Theorem, is that you can have something kind of complicated, bring it down to a line, and then, well, decide that you have 4 lines to parameterize for your line integral. Why don't we use that boundary for the line integral and make another surface, a simpler surface, that would have that same boundary as this complicated 5-surface thing that we have. So now let's take a look at this. This surface is only one surface. It's just that cover. And that would be a lot easier to do a flux on one surface than on 5 surface. Or it's easier to do a flux on one surface than line integrals on 4 curves, 4 lines. So I think we'll go with this one. Okay, so let's parameterize this. This is the bottom part of the box. So, and it's parallel to one of the coordinate planes, so one of them has to be constant. Which one's a constant? Z is equal to? It's down below the xy plane at -1. And then this looks like it's just a square, rectangular region, so I can just call x and y, y, and then I'll have limits for x and y. What are my limits for x and y? -1 to 1, -1 to 1. So that's it. Looks like it'll be an easy integral to me. I don't know if we need to do this, but well, I'm not going to do it. Can you just tell me what the normal vector should be? K. Well, we want the orientation for this. We want the orientation for this to go around in this direction, right? And so we're going to want the orientation. We're not putting the cover on for the sake of putting the cover on. What we're doing is we're kind of shrinking this box into a square. And wherever the box was oriented the first time, the new square would be oriented in the same direction. Okay, so it's not a cover per se; it's a replacement for this. Yeah.
Why do we want to go that direction?
Because according to this box with an outward orientation, the 4 lines, the boundary is going in this direction. And as the boundary goes in that direction, we want to recover the surface again, and the orientation for the surface goes up. Okay? All right, so let's take the cross product. And you know what? If you think about taking the cross product here, you already know that the x and the y terms are 0. You really don't have to figure out the x and y terms of the cross product. I mean, of the curl. You can if you want, but that's going to go away. You know what I mean when you take the dot product? I'll show you what I mean. So the curl of f is going to be on the x component. I don't care what that is. On the y component, I don't care what that is. On the z component, on the z component, I would take the derivative of this with respect to x. That looks like it's a y. I'll take the derivative of this with respect to y. That looks like an xz. Okay? Why did I not care? Because in the integral, I'm going to dot with my cross product here, with my normal vector, and it has zeros in the first 2 components. So my domain is given by this. My curl is this. Oh, I need to put in the z is equal to -1, by the way, right? I need to put x in for x, y in for y, and z, -1 in for z. So let's make sure we put -1 in for z here. And then I'm dotting this with my k vector, 0, 0, 1, and then dx, dy in some order that doesn't matter because they're both constants. And so I'm really just integrating -1 to 1, -1 to 1 of y minus x times -1 dx, dy. Okay? And I actually don't have to use Wolfram anymore, because I think I could do this, right? You think? You think? With respect to x, xy plus x squared over 2 from -1 to 1. Oh, it just got hard all of a sudden. Hey, if somebody can figure it out right now, just tell me the answer. I take that as nobody's going to try. You're just going to wait for me to come up with the answer. 0. So it looks like the flux is going to be, the answer is going to be 0. Okay, yeah.
So geometrically, there has to be a reason why flux is 0 for this interval. So are the vectors going in different, like going in the same direction or something, or different directions?
Well, your curl might be going up that's perpendicular to this surface, in which case it'd be 0. Or maybe it's going perpendicular to the normal of the surface. So the curls might be going without a z component. That might be the thing that would be happening. So you see that looking at the surface, we kind of left the idea of a surface to go into the line integral according to Stokes. And then we saw that the line integral here looked like it might be a little too difficult, so we left that and went back to the surface, a flux integral, and decided to come up with an easier surface to deal with. And so in doing that, we kind of used Stokes Theorem in a weird way, in a strange way, but we got to get this to get this answer. I hope it's right. Yeah.
We did the same thing with the last example with
Yeah.
the hemisphere.
Yeah, we flattened the hemisphere down into a disk. So that's the same thing. We kind of flattened this box into a square.
Can you use this in any case with a three-dimensional surface with a boundary?
Yeah. As long as it has a boundary. Yeah.
We can just show that the curl is perpendicular to the normal. Is that
Yeah. Was it perpendicular to the normal? Oh, because the z's are gone. Yeah. Yeah. But you should go through this computation. Okay?
What do you mean by disease?
Oh, because when we did the calculations here, we the parametrization left us with z is equal to -1, and with z is equal to -1, the curl just has x and y's, and so the normal is in going up in a. But yeah, you should actually compute the integral. That was easy enough to compute.
So you had a rectangle with sides that aren't. How would you, could you flatten it in any direction further?
Well, as long as it's a boundary of something, yeah. So the thing about the flux integral is that it's looking at the surface. And the thing about Stokes is that you're looking at the boundary of the surface. So your surface has to have a boundary. If it has no boundary, then it's just going to be 0. Yeah. So the idea is that it doesn't matter what your surface is. You can always redo your surface to just be the disk or the square or something flat that would be contained in whatever that boundary is. And then you can integrate Stokes using that surface instead of this more complicated surface based on your boundary. I don't know. Are we good with this? Yeah?
What happens if there's more than one?
That would be a. Trying to see if there's a problem like that here. Then you would have to consider those two as boundaries. You would have two integrals, two line integrals. So let's think about that. A common type of problem would be one of these cones that would be kind of cut short. So they just have this piece of the cone. So this cone has two boundaries. So if we take a look at like this cone with an outward normal, for example, if this is S, then your flux of the curl over this S is going to equal to, because this thing has two boundaries, two holes, is going to equal to the line integral of the two boundaries. So C1 and C2. So this is going to have to equal to two line integrals. What? No, because this went down to.
Oh, sorry. Yeah.
So we need the orientation. So what's the orientation for C2? If this is an outward normal, right? Orientation is going to, from this front end, is going to push it to the left or to the right? To the left. It's going to go this way for this orientation. Now, if we go down in the bottom, is it going to have the same orientation? It's going to have the opposite orientation. So that's why for these things, you can't really consider clockwise or counterclockwise anymore. You can say clockwise looking from the top, but that's more, when you talk about the positive orientation, you just have to draw the orientation. So this is what you would have. Yeah?
So whenever you have a hole, the area vector of that hole, if you could consider the surface of that, would be going in towards the surface.
Say it again?
So, like, if you make like an area for that curve, for each of those curves, and make that an area,
Yep.
the area vector is going to be pointing in toward the surface itself.
So if it's going this way, the right-hand rule would make it point, the orientation point down. And then for this one, it would be pointing up or down. It would be pointing up.
Isn't that true with the outward orientation?
I don't know. Maybe. Yeah, I don't know. You can think about it. Okay. Any questions? So that's Stokes. I think that's about all we need to say about Stokes Theorem.
What chapter is it?
16:8. Okay. Now let's take a glimpse of Gauss. So Gauss's theorem is sometimes known as the divergence theorem because because it has the div divergence operator on there. So now we're going to a triple integral. E is a simple solid, and S is the boundary of the solid. So you got a solid now, and then now you have the boundary of the solid given with a positive orientation. So the boundary of the solid is closed. And then F is a vector field. Partial derivatives are continuous in the region that contains E. Then this flux integral is equal to a triple integral. Triple integral of the div of F. So div is some form of derivative. So if I say this again in those words that I've been saying all along, the integral of a derivative of a function over a solid is equal to one less integral of the original function evaluated at the boundary. Same thing, fundamental theorem of calculus. So maybe we can write this a little bit differently. So the div of a vector field is what? A vector or a scalar function? Scalar function. So this is a scalar, and so those single, double, and triple integrals that we've had take in scalar functions. And then this is going to equal to the flux of the boundary of the solid. So this is essentially a closed surface. So when we talk about a closed surface, sometimes people put a circle around the two integrals to say that this is a closed surface with a positive orientation. Put an arrow around that circle going counterclockwise of the original function dotted ds. So this is a flux integral. Okay. Any questions so far? Should we do an example? So let's compute the flux of a vector field. Let's keep the vector field simple, x, y, z. Over the surface, over the sphere, radius, I don't know, pick a number. 4. Centered at the origin, let's just go with the standard sphere. With outward normal. Orientation, I guess they call it. So this might be easy enough to do directly, right? It's a flux over this sphere. So x, y, z, ds. So we'd have to parametrize a sphere. We might use spherical coordinates to parametrize that. But instead of going about it this way, let's use Gauss. And instead of doing a flux integral, let's see if doing a triple integral would be easier. So Gauss's theorem says that we need to look at a solid. What's that solid going to be? It's that solid sphere, right? So S is just the surface of the sphere. E now is the whole solid inside of the sphere. And then we need to take the div of F. Remember how to take the div? What's the div of F? Wait, is it a vector or a scalar? So what is it? All right. So it's the partial of the first component with respect to x plus the partial of the second component with respect to y plus the partial of the third component with respect to z. Well, that's nice. It's a constant. Let me rewrite this integral again. If it's a constant, we could take it out of the integral. What is this triple integral? It's the volume of the sphere, right? So what's the volume of the sphere or radius for? Cube? So our triple integral, usually triple integrals seem like really scary and hard and stuff, but in this case, we got the triple integral, and just the div happens to be a constant that you could take out, and then now we just have the volume of the sphere, which we just rely on some simple formula to figure it out, and then we get this thing. So this is our answer. So instead of doing a flux integral, parametrizing the sphere, and dotting it with x, y, z, and doing all that mess, we were able to compute this using the divergence theorem or Gauss's theorem by a triple integral, where our div became a lot simpler for us to deal with, and then our triple integral turns out to be not even an integral at all. Yeah? No, no. Not always. That would be nice if it was, right? But, you know, it's always good to have a simple first example. Hopefully your final exam will have a constant for a div. Oh yeah, hopefully. I have this special problem. What? No, like your first two exams have those special problems, like the projectile for the first exam and the ant for the second exam. For the final, I have a special problem I like to refer to as a flashlight. Yeah. So just to give you a little preview of my special flashlight problem. A flashlight can be made with just a bunch of surfaces. We'll start off with a cylinder, a cone, another cylinder, and a hemisphere. So this would be the surface, and then we would do stuff like, find the flux of the curl of the surface, or find the flux over the surface and stuff to take advantage of Gauss's and Stokes Theorem. It'd be nice if you can parametrize this, and I usually give this as extra credit, but you guys have a lot of extra credit already. So. Do I have it here? I have it somewhere. Nah, I can't find it. Anyways, parametrizing these things would be a good exercise. So it's like I said, a cylinder, a cone, a cylinder, and a hemisphere, and there's a lot of shifts going on. So if you can parametrize that, that would be good. And then we can assume that this is on the XY plane. And we just need to give different values for the heights of these things. So imagine if this was an open surface, how you would use Stokes Theorem. And also imagine if this was an open surface, how would you use Gauss's theorem? So Gauss's theorem is a little trickier because Gauss's theorem, according to the theorem, we're looking at a closed surface. Okay, so that's something interesting to think about, to help prepare for your test. All right, I think I'm done. We'll have more applications for the divergence theorem next time, and then we'll relate it to another version of Green's theorem called the divergence theorem on the plane. We'll bring it down to 2 dimensions again. All right, see you guys next week.